Okay, so this morning and this next week's lab, I've put a lot of time in these past 2 weeks changing the lab and making it more understandable. I built this spreadsheet to simulate the spectrum of a particle in a box, and it's pretty enormous, okay, because I wanted to have nice smooth curves. And so my wave functions were plotted where the box is divided into 200 increments. So it doesn't all fit on the screen. And that was a big problem for the students. Many of you are learning Excel, and for you to have to scroll down, page after page and so on, it just eventually is overwhelming. It would take about 8 hours, so 2 lab sessions, to get through building this spreadsheet. So I've spent about 4 days in the afternoons. You've probably noticed it's been hard to find me in the afternoons. I've been disappearing to try to work on this spreadsheet so that you guys would have a better educational experience next week. So we're combining the 2 Excel labs into one and making it smaller. And so we're going to really talk about that a lot today. In fact, we're going to go to Excel, and I'm going to essentially walk you through what you're going to be doing next week. What we're doing is the third part of this course on spectroscopy. The first part was calculus week, understanding spectroscopy analytically, so doing the actual integrals. The second part was group theory and seeing how symmetry can really reduce the amount of work. But what did we lose when we went to symmetry? Let's see if you notice this really subtle point. Okay, in calculus, we're able to calculate the analytical result for the spectrum, but we lost something when we went to group theory. Yes, what do you think?
Intensity?
The actual intensity. We only got 0 or non-zero. So when that integral's non-zero, we know there's going to be a peak there, but we don't know how strong it is going to be. Now we can kind of say if it's a delta n of +1 or -1, it's going to be a stronger peak than if it's delta n ±3 or ±5. We saw that, but we'll definitely see that next week. So the third deal is to do this in Excel numerically. So the integral is just a sum, and Excel can sum a column of numbers. And now it's not just the sum of y, it's multiplied by dx. And so we're getting sort of a column graph. We're turning our smooth curve into a bunch of little areas, a bunch of rectangles. And you can sum all of the y values of those rectangles and multiply by dx and get the integral, the area under that curve. So we can do integration in Excel. You can also do differentiation. What's the slope of a line? Rise over run. So delta y over delta x. And with those 2 tools, we can do the whole Schrodinger equation, solve for the transition dipole moments, actually get the intensities. And there are some functions in Excel that save us a lot of time. Things like sum product. So you have 2 arrays, you just use sum product. It will take those arrays, multiply them by each other, and add them together. And so sum product is a great way to do an integral in Excel. And I'm going to show you that this morning. And also, matrix multiplication is a way to do sum product for a block of columns. So you can take a bunch of columns of data and flip one, multiply it by the other columns of data, and it will add them all up and give you every combination added together. So it'll do integration of whole blocks of columns for you, just using matrix multiplication. So you'll learn mmult, transpose, and sum product today in the numerical methods. So let's talk a little bit about what we mean by numerical methods. So we have this perturbed wave function. So on the left is our ground state, the blue curve, and on the right is x times that blue curve. And it's perturbed that wave function, and now it's changed the symmetry. It was even, now it's odd. And if you look at that function times, say, the n equals 2 state, they're compatible now. There could be a symmetry allowed transition. And so we're looking at these perturbed wave functions, and that's part of the transition dipole moment integral. This transition dipole moment integral that we've been talking about this whole time is proportional, the square of it is proportional to intensity. So we're just using that as our intensity value. But if light comes in and can cause a transition from, say, 2 to 3, there won't be a transition from 2 to 3 if there's no atoms, molecules, or particles in state 2. So we need to figure out what the thermal population is. There's always going to be population in the ground state. So even at 0 Kelvin, And this is an interesting thing. I asked this question on the exam last year. I think this was on the final exam, and I was sad. That's where half my hair went. I asked at 0 Kelvin, what's the probability of this peak happening or whatever. And the students in Excel would type in 0 Kelvin, and the peak would go away. So they wouldn't see any transitions at 0 Kelvin. Well, that was a mistake of an Excel. You were somewhere in those formulas, you were dividing by 0 and getting an error. So at 0 Kelvin, there's only one transition. It's the fundamental. So the fundamental is always there, even at 0 Kelvin. It's the hot bands that go away when you cool things down. So the hot bands go away, and you're just left with the fundamental transition at 0 Kelvin. So since everybody missed that on the final, I want to make sure that you get that. So even at 0 Kelvin, you have the fundamental, because all the molecules are in the ground state. But for hot bands, you need this Boltzmann distribution, and you need a high enough temperature to get molecules thermally populated in 2, 3, 4, the higher excited states. So let me just visually, I've animated the different curves to kind of show you what's going on with this numerical integral. So we have wave function x psi 1. So that was the ground state perturbed by light. And so now it actually looks like n equals 2, even though this was the ground state wave function times x. So that's what we get. And then we can look at wave function 2. It's actually pretty small, but it's this green curve. It's positive on the left, negative on the right. And if we multiply these by each other, we have a negative times a positive is going to give us negative, and negative times a positive is going to give us negative. So that's the two functions multiplied by each other. And then if we integrate this and square it, so we're summing the squares of the product here, then we get this integral. And so that's what the integral looks like from the left side of the box to the right side of the box. And when you integrate it over all space, that's the transition dipole moment integral. And the result is 1300. So the n equals 1 to n equals 2 level, this is for a 7 angstrom box and an electron, that you get quite a large transition dipole moment, 1300. Looking at wave function 1 and 3, so this is going from the ground state to the second excited state, or n equals 3. Here's the integral. In the middle of the box, you've got some non-zero results, but at the end, the positives and the negatives cancel out, and you end up with a transition dipole moment integral of 0. And you may ask, well, what happens in these interior regions? It's really not a valid experiment. You have to integrate over all space. And so we're looking at how it behaves across the whole box. And so when you integrate from left to right, when you get back over all the way over here to the right, your result is 0. One more, we have 1 to 4. So this is going from state 1 to state 4. And you do the integral. It's a really strange looking integral. But it comes down, it doesn't go to 0, it goes to 8. So this is the first overtone, 1 going to state 4. And it's got a much smaller probability. The 1 to 2 was 1300, 1 to 4 is 8. And so let's learn about arrays, because we're going to go into Excel next week, and you're going to be dealing with columns and rows of numbers. So any kind of column or block of numbers is an array. And these are some of the tools that we're going to learn. We're going to learn about manipulating the arrays, like transposing them, and then matrix multiplication and numerical integration. So any row or column or block of numbers is an array. Like this. This would be what's called a row vector or a row array. And this is a column array. And so let's learn by inspection. So what's going on here when I say transpose? So if I transpose that row array, it becomes a column array. So that's what we mean by transpose. And it rotates around the diagonal. And the upper left, now when I say upper left, I'm thinking of a matrix, but even in a row array, the farthest left value, that's what it's kind of rotating around. And if I transpose a column array, it becomes a row array. And so there's a transpose function in Excel that's very important for us to use. Let's do this for a matrix. So for a matrix, we can rotate around that diagonal. So if we transpose this 3 by 2 matrix, it becomes a 2 by 3 matrix. So notice A and E are still in the same positions. It's the ones below the diagonal became on top of the diagonal, and the ones on top of the diagonal went below. So this is the transpose of a matrix. A matrix is just a 2-dimensional or even 3 or 4-dimensional array. So in Excel, we would type in transpose, and then we would select with the mouse that set of values A, D, B, E, and C, F. And once you select that, then that would be put into the transpose argument parentheses. And then in terms of the result, you have to select. So you select these 6 cells first, and then you type in equals and transpose and open parenthesis, and then you drag your mouse over these 6 cells, close parenthesis, and then hit Control-Shift-Enter, because Excel needs to put that formula in all 6 of these cells. So unless you use the Control-Shift-Enter, you're going to get an error. And so that's another thing that you need to learn in Excel. Whenever dealing with array functions, and this is an array function, you need to use Control-Shift-Enter. And you need to predict how big that array will be and what the shape will be. So if you're looking at this and you want to transpose this 3 by 2 block, it's going to give you a 2 by 3 block. So 2 rows by 3 columns. And so you would select that block because that's what it's going to fill up. Then you type equals, transpose, and then open parenthesis, and then you select the block of numbers that you're going to transpose. Close parenthesis, Control-Shift-Enter, and then it does it. We'll learn by doing here in a second. I'll show you. So array multiplication. So now we're taking this row array and multiplying it by this column array. And look what happens here. So I get 1 times A plus 2 times B plus 3 times C. So it takes that row times the column and adds everything together. That's sum product. So you're also taking this array and that array, multiplying every term by every corresponding term and adding them together. And you get a single value, so you don't need to use Control-Shift-Enter. And so in Excel, you could do sum product. You could have the cursor here, hit equals, type in sum product, open parenthesis, then you select array 1, comma, array 2, close parenthesis, and just hit enter, and you get the integral of those 2 arrays multiplied by each other. Now for a matrix multiplication, this is a little more complicated, but if you think of it as multiple sum products, so 1, 2, 3 times ABC would give you 1 cell value. 1, 2, 3 times DEF will give you the next one. So if I take this first row times the first column, I get this first value in the result. If I take this first row times the second column, I get the second column first row result. If I take the second row times the first column, I get the second row and first column result. And the second row times the second column, I get the second row and second column result. So I've done, with just this operation, I've done 4 integrals. I've done every possible combination of column times column added together. So you can see how this would be really fast. If I wanted to integrate 15 wave functions, I could select that block of wave functions. I would transpose it so that the rows and columns work out. And then I would hit a comma and then select that block of wave functions again and hit Control-Shift-Enter, and I will have done 225 integrals with just 1 keystroke. A lot faster than doing it by hand, 6 pages of paper, analytical method. Okay. Yeah, so that's why we like Excel. So we didn't just do it for 1 transition dipole moment, we did it for 225 of them. Now y'all are going to do it for 4. Okay, so you're going to have 2 wave functions times 2 wave functions, and you're going to do mmult, and you'll get a 2 by 2 matrix, and you'll be able to see the pattern. Okay, so Now, let's talk about matrix multiplication because there's some rules that go along with it. The patterns have to match each other, the rows and columns. So you have M1 times M2 equals M3. But each matrix is a row by column. And so I've color-coded this. You will probably want to print this off someday or go back and find it because you're going to run across matrix multiplication and think, I can't remember the rule. But I remember Dr. Williams talked about it. And so you're going to want to find this slide and go back to it because it's beautifully color-coded. Okay. So the matrix 3 is going to be the rows of matrix 1 by the columns of matrix 2. So that's how big the result is going to be. But in order to do the multiplication, the inner values have to match. So columns of matrix 1 have to match the rows of matrix 2 because it's going to take that column, tip it up, and multiply it by the rows. And so those lengths have to match. So the columns of 1 have to match the rows of 2. So that when you do this matrix multiplication, the lengths match. And then you sum them together and you get a value. And so if you notice this, a 2 by 3 can be multiplied by a 3 by 2, and the result will be a 2 by 2. And that's what we saw on the previous slide. And then these columns, the inner columns and rows have to match. The 3s, that they satisfy that rule. Okay. So, and in Excel, this is how you type that in. So this crazy business, you just type in, you would select this. Let me go back. Come on, help me out here. You would select this 2 by 2 square block in Excel and type in equals mmult, open parenthesis, and then with the mouse, select A1, hit a comma, and then with the mouse, select array 2, close parenthesis, Control-Shift-Enter. And there you get your matrix multiplication. So here's a pictorial view of it. So here's your 2 wave functions that you guys are going to have. We're going to use transpose inside because you're going to just have a column of your wave functions here. And you're going to select this 2 by 2 square. And you're going to type in equals mmult, open parenthesis. And then you're going to type in transpose. So we're combining the 2 functions. And you're going to select psi. So you'll select those 2 columns. But what you're really doing is you're producing this. Right? You're producing a transpose of that block of numbers. Now I've shown you with the picture the headings. Don't include the headings. Okay, but I just wanted to show you what those numbers were. So you would just select these numbers. You would say transpose, open parenthesis, select these 2 columns of numbers, close parenthesis, comma, and then select these columns of numbers again, and that's this side, close parenthesis, Control-Shift-Enter, and you will have done 4 integrals. Now what we have here, if you notice, this is psi times psi. Remember we have the wave function times itself? What's the result of that? 1, if it's a wave function times itself. What if it's the wave function times any other wave function? 0. Can you see Kroneker's delta here? Wave function 1 times wave function 1 is 1. Wave function 2 times wave function 2 is 1. Wave function 1 times wave function 2 is 0. And wave function 2 times wave function 1 is 0. So you can see those results here. And that would be one of the lab questions. Can you do this matrix multiplication and see Kroneker's delta in this result? You know, and it's the diags are 1 and anything off diagonal is 0. If you get something non-zero in the off diagonals, then you've probably included something wrong, you know, or you haven't gone all the way to the bottom, or something's, you know, it's a clue that something's wrong. And so let's go to Excel and do this, but first let's do the Kahoot. So pull out your phones. This is just a review of the Milliken notation, identifying the Milliken notation. And so you'll probably want to bring up the benzene character table, the D6H character table. The D6H for benzene. It's like a 6-question Kahoot. And I've drawn benzene up here, and I've drawn the coordinate system. So the z-axis comes out of the board. X is in my direction, y is going up and down. But these 6H, because you'll need to identify the Milliken notations. So which row of the character table is this? These different orbitals. Sorry, I'll get back to it. Make sure. Okay, good. All right. Okay, that's everybody. So you're going to look at the picture up here, and you're going to find that row on the character table, and you can use that little flow chart. So these are all the 2s orbitals on the carbons, and they're all in phase with each other. So left and right are the same, top and bottom are the same, front and back are the same. It's totally symmetric. Very good. A1G, that's the top row of the character table. And whenever you have something that has no nodes, it's totally symmetric, it's probably going to be top row. Because no matter what you do to it, it's going to be +1, all of the different symmetry elements. Okay. Here's the coordinate system. Just pick one of those, doesn't matter which one, and go through it. These have the same energy, so that's a clue as well. Sounds like we're in Bowser's Cave or something. Da-da-da-da-da-da. I thought there were 27 players, and we have 27 answers. How come it's not?
You got an extra student?
That's right. Somebody must have got in. Yeah, so it's E1U, okay? All these were U. Why were they U? Let's look up here quickly. What does U tell us? Even or odd? Odd. What does that mean? It's under inversion, the I. So that means if you invert this, everything changes sign. So the blue and the yellow swap places, and so that means it's going to be U. And so that's another clue that you can use. But you couldn't really use it on this one because all 4 answers were U. But if you have a choice between Z or U, if you look at this one, it's going to be one of the U answers. Okay. So. Gets a little more tricky. Here's the axis. Try look at the one on the left and try that pattern recognition that I was talking about. Left is different than right, top is different than bottom, the front is the same. So just ignore the z-axis on this one. Do you see the plus minus pattern in the 4 quadrants? What does that tell you? Okay. So the yellow on the one on the left would be, say, positive, and then blue would be negative, and then down here would be yellow again, so that would be positive, and then the right would be negative. And I identified a particular function related to that pattern last time. So this is my test of knowledge retention. Let's see if you remember. Okay, well, that's good. It's a majority at least. That's the XY pattern. So X times Y. So this side would be positive. X times Y, this would be negative because you have negative values times positive values. Down here it's negative times negative, and here is negative times positive. So it would go around positive, negative, positive, negative. Now what about the one on the right? What would that one be called? There's also a, you can look at the character table to see what it's coupled with, X, Y. X squared minus Y squared. So notice the yellows are the same. So X would be the same with positive and negative, so that's like X squared. And then it's a different color than the Y squared. So this is X squared minus Y squared if it lines up with the axes. And if it's between the axes, it's XY. So they have the same energy because they're just rotated 45 degrees. Okay, this last one's the worst. My flowchart fails on this one. Yeah. So when it says investigate further, here you go. So look at the character table and see if you can figure this one out. You've got 4 choices here, so you can ignore most of those rows. This is going to be pretty random, I'm sure. But see if you can figure it out in 90 seconds. What tools would you even use to figure it out? Look at the columns. Every one of those columns is a symmetry element. So if you rotate it and the colors don't change, that's a +1. If you rotate it and the colors change, that's a -1. So if I rotate it 1/6 of a turn, the colors change. So I'm looking for a -1 under C6. Does that help? Okay. If I rotate it 1/3 of a turn, the colors don't change, and that's a +1 under C3. What about inversion? If I invert this, the colors change. So it's -1 under inversion. I thought 90 seconds might be enough time, but it's not. Yay, good job, 16. Okay, so that's what I mean by investigate further. Sometimes that flowchart doesn't cover everything, and you've got to go through the character table and see how the colors change. If that blew your mind, talk to your TA during lab, have them show you that, and also talk to each other if some of you guys have figured it out. Okay, great job. Okay, so now let's go to Excel. This is the spreadsheet, the blank spreadsheet that you guys are going to do. Let me zoom out and show you how big it is. It's not that bad. Okay, it's better than the one I had. Okay, so the spreadsheet is pretty well constructed for you. And so you're just going to walk through. There's very specific tasks identified. There's 17 of them. And then I'm working on the discussion questions this afternoon that you'll have to answer for your lab report. Okay, so let's go up here and we'll just I'll quickly go through some of the tasks and then you'll get to do them yourself. This is also a tool to teach you Excel. So if you don't know Excel, that's fine. You're going to learn some skills today. We've already talked about array functions and sum product and so on, but you'll also, the most important skill to have is anchoring cells. And so F4 is the key to use for anchoring cells. Right in the middle of benzene. F4. To anchor cells. Why are anchored cells important? If I'm going to use Planck's constant or L in an array, let's think about the wave function. It's got square root of L/2. I'm going to reach up there and I'm going to poke the cell that has L in it and I'm going to hit F4 so that when I copy that formula down, it doesn't drag down the reference. and get off of L. So I hit L and I anchor it so that no matter where I copy that formula, it always refers to L. And that's the most important thing that you can do in Excel is anchor your constants. And so then if I want to change L later in the day, I can make it 8 angstroms, and every formula in the whole sheet changes. The energies change, everything reacts. So this is not just better than the calculus week calculus. It's dynamic. So when you're finished with this spreadsheet, you want to know what the energy of the 50th wave function is, type in 50 for n. It actually won't work on yours because you only have 10 rows, and the 50th wave function changes so much it's going to be bonkers. But you'd have to actually have 1,000 rows to get a good energy for 50th, for n equals 50. But you can just take what you've done here and expand it 1,000 times. So let me zoom in. The very first task is to analyze the wave functions. So I've built this in to where you've got the box length right here. So the yellow cells are the ones that you can tinker with later, okay? And you've got the particle mass. Let's focus on the box. So here is a very important cell. This is dx. So whenever you're doing integrals and you have the sum times dx, that's the cell to use. You go over, hit that cell and hit F4 and you anchor it. So sum times dx, that's dx. How do I know dx? Well, it's the length divided by 10. So I've got this box defined here. There's 11 values because it includes 0. So I've got my box divided into 10 increments. That's my x-axis. And so let's type in the wave function. So this is equal. Can you see that? You will. You'll certainly see it on the video, and that's why I'm videoing this. Is equal to the square root SQRT, so there's a function for you. 2 divided by, let's come up here and get L, and I hit F4. So let me scroll down so you can see what happens when I hit F4. See, it says D5. That's called a relative reference. If I hit F4, it becomes an absolute reference. It's $D, $5. So I hit F4 and it anchored it. Close parentheses. So I've taken the square root of L over 2, or 2 over L, I mean, and I'm going to say times sine, open parenthesis, and I need n pi x over L. So right up here is n for this first wave function. I'm going to anchor that one, but I don't want to anchor it absolutely. I just want to anchor the row, because I'm about to copy this formula over, and I want that reference to move over to capture 2. So I only want to anchor the row. So I hit F4 once, I hit it again, and it anchors the row. If I hit it a third time, it anchors only the column. And if I hit it a fourth time, it goes back to not anchored at all. So you can just sit here and hit F4 until you get the column, the row, or nothing, or everything. So I do that too sometimes. I go too far, I'm like, oh, I've got to keep going. And finally, I have to use both hands because I have to function. And anyway, it's my laptop. Then I hit times. Now pi. Now pi, you don't have to type in 3.1415982 and so on. Just type in pi, open and close parentheses. So Excel has pi to who knows how many digits. So pi, open close. And it's a function that gives you pi. That's nice. Okay, then times, and I want to get the x. I just hit left arrow and it went left. And I'm pointing at x now. Now for x, I don't want to anchor the row because I'm going to copy this down. But I do want to anchor the column. So when I copy this over, it stays over on x. So when I copy this wave function over to wave function 2, I want the x column to stay the x column. So I hit F4 once, twice, 3 times, and now I'm anchored to B. The $sign's in front of the B. So that means it's going to anchor it in the B column, but it's going to let the row move. Okay, then I say divide by L, so I got to go up here and get L. And I want to anchor everything on L. I don't ever want L to move. Okay, so that's the first part of the wave function. And then I've got to add in the little phase shift. So plus n, so I got to go up and get n. Again, I'm going to anchor the row times pi, divide by 2, close parenthesis, enter. Good. And then I come over here and I grab this corner right there and drag down. That's neat. Yes? That's my wave function. Now, I don't have to type that again. I can grab this corner and go to the right, and if I've anchored everything correctly, it's going to keep the columns where the columns need to be, and the rows where the rows need to be, and L where it stays put. Now let me show you another way to copy this down. You get down here where you see this little plus, and you double click. And if there's a column of numbers next to it, it goes zip, straight down. Okay? So let's plot these quickly. Grab the x values and the two wave functions, insert. Over here is a chart type. XY scatter, write that down, XY scatter. And I want lines, straight lines only. Okay? Never, never, ever use smooth lines. Okay? Minus 10. Serious, I don't like smooth lines, yes.
What does smooth lines look like?
It's up here. It's these. It says smooth. Okay. It's using a spline function, and it's not telling you what the spline function is. So if you plot a line on a chart, this is just scientific. Any science. If you plot a line on a chart, you better be able to produce the equation for that line. And if someone says, what's the equation for that smooth, briefly line? And you go, I don't know. Then you're in trouble. But if it's a fit, you can produce slope and intercept and all of that. You know this. And if it's just connecting, like it's straight lines, then all you need are 2 data points, and you know the line that connects them. So you can give me the equation for every segment. It's just the linear line that goes between those 2 data points. So that's just my pet peeve, but it's a scientific pet peeve. So there's our wave functions. That was a piece of cake. So that there is task 1, use the constants to make the wave functions. Task 2, plot the wave functions. Task 3, produce some products, okay? So, and also, this is kind of cool, I made some Boolean logic down here to check to see if they're even and odd, and so it tells you if it's even or odd. So that's kind of neat. Proud of that. Okay, so let's look at wave function 1. Let's just do this one. Let's say equals that times that. So that's that psi n squared. And then let's do equals that one times the one next to it. So we've got the first wave function times itself, and then we got the first wave function times the second wave function. And let's do the integral. Equals sum. Come over here. Let's grab that one and go all the way to the bottom. Close parenthesis times dx. And here's my dx. And I'm going to hit anchor on that just for fun. Okay. Boom. So wave function times itself is 1. So that's the normality condition. All right, let's sum this other one. Equals sum. Okay, I'm going to go left with the arrow. Now watch this one. Control, shift, down arrow. Watch what it does. Control, shift, down arrow. So it just shoots down to the bottom and it's got everything. The shift part is the select. If I just hit control down arrow, it just moves down. It doesn't select. Okay, that's control up, control down, control up. But I get over here and I do control shift down. The shift selects everything. And then I hit close parenthesis times dx. Grab dx. Enter 0. It's orthogonal. 1 times 2 is orthogonal. We could have done the same thing with sum product. Equals sum product. You can hit tab here and it'll open up the parenthesis. And I grab array 1, comma, array 2, close parenthesis. So you see your 2. Oh, I'm supposed to do the 1 times itself. Oh, okay. Yeah, let me back up. We'll just, because I'm just going to do this xn squared. Okay. And so we'll grab that one again. So times dx.
if you're going to integrate, you better do your dx. If you forget that, then it's not going to be good.
So there it is, 1 times itself. Now let's do M mult. So already I've kind of built the spreadsheet for you, so you know it's going to be a 2 by 2. I have 2 arrays times each other in all combinations. So I type in equals M mult, M-M-U-L-T, open parenthesis, transpose, open parenthesis, and I select array 1. So I get both wave functions, okay? Close parenthesis, comma, so that's the transpose piece, and then I select the wave functions again. Close, and then what do I have to hit? Oh wait, let's gotta do dx. That's right, let's do times dx. And then Control Shift Enter. Isn't that great? Do you see conic delta in the matrix above? Yeah. And so those are the main skills that you will repeat for the transition dipole moment integral and all the kinds of things. Just doing this analysis of the wave functions, now you're set up to finish the lab, and it's just much easier than last time. And so you can look up here, we've done task 3, the products, task 4, take the integrals, look at orthonormality with the matrix multiplication. So then we go over here and we look at the next thing is solving, solving the Schrodinger equation. Okay, now for this one, we're going to take derivatives. And whenever you take differences, you lose some rows, right? Because you're saying this times that number, delta y divided by delta x. Since it's deltas, we're going to lose a y and an x every time we take a derivative. And we don't want to shift the curve. If I'm looking forward and I say, let's do it this way for your perspective. If I'm taking x0 and I'm looking at the difference of x1 minus x0, where do I put the result? If I put it on x0, I've got the forward difference. If I put it on x1, I've got the backwards difference. I've got x1 minus x0 plotted at x1. But either way, I'm shifting that difference. I'm either shifting it back a value or forward a value, and that 0 is going to shift, and it's going to break the symmetry of our wave functions. So we want to take center differences. If I'm at x1, I want to take x2 minus x0 and plot it at x1. So now I've got two differences, and I've got y2 minus y0 plotted at x1. So that's what's shown here. That's called centered differences. So I have the wave function at xi plus 1 minus the wave function at xi minus 1 divided by the difference between those things in x, and that's going to be plotted at y. So you can follow these little I values. Let me just do one here. So let's go grab our wave function. We've got 2 minutes, so hang with me. Okay, copy this wave function. Let's go put it over here. It worked. Okay, thank goodness. Okay. Copy. Paste this down. And notice we've expanded our box 2 cell values above and below the box. I'm going to say paste values only so I don't screw up my little paste function.
There's no value on
Yeah, something's wrong.
You put paste for me.
Okay, so something's not anchored right. It got the quantum number, but what I'm trying to show you, let's go down right here. I'm trying to show you that we're going to have the wave functions plotted here, and then when we take the first derivative, psi prime, it's going to be like psi prime right here is going to be based upon this y difference. So 2 minus 0 is going to be plotted at 1. Does everybody follow that? I want to see eyes. So psi 2 minus psi 0 is going to be plotted at 1. Okay? And then that's the first derivative. Then when I get to the second derivative, it's going to be 3 minus 1 is plotted at 2. With every derivative, we lose a row on the top and a row on the bottom. So we do the first derivative, our table's 1 row shorter on the top and bottom. Do the second derivative, it's in the box now. And so that box that I've drawn on there is the box. But we had to go past the edges of the box so we could do our 2 derivatives. Okay? It's just a feature of the derivatives trying to maintain that symmetry. Because if you maintain the symmetry, then your zeros and your non-zeros are going to be just right. If you shift that symmetry, you're going to have what look like small values when your selection rules will be screwed up. And so we want to maintain that symmetry by doing these center derivatives. That's probably the most confusing part of the spreadsheet. But if you've got this, that whenever you do the derivatives, you lose a row on top and bottom, that's really all you need to know. Okay. And the formulas are all up here. So you've got to figure out how to translate this mathematical formula into Excel speak. And your TA can help you with that. All right. So I look forward to next week's lab experience. It will sort of cap this whole spectroscopy analysis for you.